Howdy everybody, welcome back to Lab Hours. Today we are talking about the confidence intervals mini lecture. That is to say, we're going to be talking about confidence intervals. The Tommy triple that I have for you today touches on estimator variance, which is going to be kind of a throwback to the last mini lecture in a lot of ways, but we're going to talk about how we handle it. We'll then talk about critical values and building the actual confidence intervals, what they are, what they do, what their purpose is, and so on and so forth. Let's go ahead and jump right in. Estimator variance. So, you'll recall that last time we talked about a certain estimator x bar, which is meant to estimate an average, right? And we remember that we gave the formula as being the interval, 1 over n times the sum of xi, for I equals 1 to n. So basically add up all of your observations, divide by the number of observations that you have, and that's your estimate for the average, right? And you remember that we showed that x bar is a pretty decent estimator for mu, or a population or parameter average, right? X bar estimates mu, right? But you'll also recall that X bar had some variance in it, right? X bar was distributed normally with a variance of sigma squared over n. And so we run into this problem, right, where we're trying to solve cool problems, or we're trying to find cool statistics about the world, but the ways that we are trying to get there are not perfect. We don't have perfect telescopes, basically. So how do we deal with estimator variance? Let's give a thought experiment. Let's give an example to sort of illustrate what the trouble is that we're dealing with here. Say, for example, you have two polling services, right? Ameripoll and Pollmerica, for example. And both of these two institutions are interested in finding out what is the average number of bananas that a U.S. citizen eats in a year, right? So let's say that Ameripoll surveys 5,000 people across the United States. And let's assume that their sample is representative of the United States as a whole, and so on and so forth. It is their job to do good polls, after all, right? They sample 5,000 people from across the United States, and they report that the average American eats 30 bananas per year, and then they give margin of error as 2 bananas, right? And then let's say that Pollmerica surveys 10,000 people, and they say that the average American actually eats 29.2 bananas per year, with a margin of error. Let's say this one is 1.5, okay? The question comes up, who are we supposed to believe? Right? Do we believe Ameripoll? Do we average 30 bananas a year? Or do we average 29.2 bananas a year like Pollmerica says? I mean, Pollmerica surveyed more people than Ameripoll. Does that automatically make their number better? The answer is potentially yes and potentially no. Here's the deal. Check this out, okay? What does this margin of error tell us? What are they even doing? Well, both of them are using the same estimator. They're using an X bar here because they're trying to report an average, right? Ameripoll ran X bar with 5,000 as the n, and their XIs are different than the XIs that Pollmerica picked up. They also have 10,000 as their n, right? But all their XIs are probably different, right? So what they're trying to say is that we found this estimate for an average. We found 30, right? But we also need to deal with the fact that there is variance in our estimator. What that means is that because we couldn't survey infinity people, we don't know for certain that our X bar is directly equivalent to mu, right? Because if we surveyed 1 million people, or 1 billion, or an infinite amount of people, the variance in the estimator would become 0, and that would make it a constant, right? Only constants have 0 variance. So X bar would be a constant that would actually be equal to mu, right? But they couldn't do that. They could only get 5,000 people or 10,000 people surveyed. So what they do is they report this margin of error. And what this looks like, if we pull out 2, the Ameripol margin of error is 28 to 32. And the Polmerica margin of error becomes 27.7. Yep. And 30.7, right? That's where they end up. What they're saying is, basically, at its most basic, they say, look, we understand that we have not sampled infinite people, okay? So we get this estimate of 30 bananas per year, but we want you to know that based on the variance that we saw in our sample and the number of people in our sample, at a certain probability level, right? And it would be helpful if they told us what probability level, but we'll talk about that in a second, right? Then we are super certain that the true average, the parameter we're actually looking for, falls within here, right? And Polmerica says, well, we're pretty certain it falls within here. So when it comes to the question of who should you believe, the answer can be both of them, right? This test, right, that they run, this X bar, and this interval that they build, says basically the parameter can be anywhere within this range at a given level of confidence, which we'll talk about in a second. And Ameripol says the same thing about their interval. So who do we believe? I mean, they're both pretty believable, and both of these estimates are actually in both of the intervals. So in reality, Ameripol and Polmerica statistically don't even have different answers from each other. So that's kind of a crazy concept to get behind, right? But Ameripol could have just as easily gotten 29.2 as their estimate, and Polmerica could have just as easily gotten 30 as their estimate. They're both within those confidence intervals. So basically, the idea that I want you to take away from this at the moment is that if a number is in a confidence interval, and we'll talk about how you pick levels of confidence and how to construct them soon, but basically, if a number is within a confidence interval, it is statistically equivalent to all the other numbers in the interval. Okay? That's something to just kind of brew on right now. We'll talk about more stuff that will help that kind of materialize mathematically and hopefully make more sense as you go along. But basically, the idea is you can believe Ameripol and you can believe Polmerica here. And we're going to show you why that's the case. So there is variance in estimators. This is one of the ways that we deal with that. Now, the one thing that I left out from this little example here is we do not know the actual confidence level of these estimates, of these intervals, right? And you might be wondering, well, what the heck does a confidence level even mean, okay? Notice really quickly, let's just use Ameripol as an example here. We have their X bar as being distributed as a normal random variable. It'll have a mean of 30, right? That's what they got as their estimate, okay? And in fact, that's not quite accurate. So we'll just not even call it that. It's, this is how X bar is distributed for them, right? So let's draw that X bar on a graph, okay? Something like this. And it's centered at mu, right? We don't know exactly what mu is, but here's the deal. We know, for example, the following things, okay? There is an interval that they have provided to us such that 28 and 32 are the bounds of that interval, okay? And in fact, this would be X bar here, right? Or 30. Now, the really interesting thing that we need to talk about here is how did they get those two numbers? Where did they get 2 from? Where did they get 28 and 32 from? Well, what they did is they took this X bar that they calculated, this 30, and they standardized it. How do we standardize something? Well, if X bar is distributed as a normal random variable with mean of mu and variance sigma squared over n, then z, or a standard normal variable, would be equal to, for example, x bar minus mu over square root of sigma squared over n, that's going to be distributed as a standard normal variable, right? With a mean of 0 and a variance of 1. They took their x bar and they standardized it, right? And when you do that and you sort of copy this graph right here, I'm going to try to not pick up the little numbers at the bottom. Now what you get is the same graph, but you'll have different numbers. First of all, 0 is going to be in the middle here, right? And then you'll have some number here, and you'll have its negative version over here, right? The key thing to look at here is going to be the following. Okay? What percentage of the area under the curve is in this little red region that we've marked? Okay? Question mark, question mark, question mark. Well, here's the deal. They picked that. How did they pick that? Well, let me show you really quick. Let's go to tmorg.org/downloads. And let's take a look at our distributions, estimators, and probability tables document from a couple lectures back. You remember this graph right here? You remember this? I remember it. Does that look strangely familiar? I think it might, right? Basically what they said is, okay, let's construct an interval using critical values. And what we want to do is we want to construct that interval such that there is a C% chance of the parameter that we were looking for being in that interval. How do we make that make sense? Okay, well, let's say, for example, I'm going to use the t-table here because it's really easy to explain this with, because we get this really nice confidence level thing up at the top, okay? And we'll just use the z-star row here at the bottom, right? This z-star row here at the bottom is going to give us the z-scores for those because we're assuming normal distribution, you know, standard normal at this point, right? So they want to say, okay, we took all of our data, okay? We took all of our data, we found an x bar is equal to 30. We found a certain standard deviation, okay? We found some, it would actually be s here, right? Or even s squared. We know that their number of observations was 5,000, and they found some s squared, let's just call it q, because we don't know what the number is, right? So they have all that data. They said, okay, we take this data, and based on this data, I want to make the interval such that the true parameter, the true average number of bananas that an American citizen eats in a year, has a 95% chance of being in that interval given the data that we saw, okay? How would I do that? Well, the first thing I need to do is I need to get the standardized numbers so that I can unstandardize them later. So let's say, for example, that Ameripol said, we're going to report the 30. That's our estimate for the mean, right? But then let's also report the interval that has a 95% chance of containing mu. So if it's not exactly 30, what does it have a 95% chance of falling in between? So let's report a 95% confidence interval, okay? So 95% confidence interval column, the z-score row gives us 1.96 as the score. I wish I could highlight it for you, but it highlights the whole page because it's a PDF, right? But they said, okay, if we set these numbers right here to be 1.96 and negative 1.96, then we know the following things. We have 2.5% of the distribution of a standard normal variable to the left of negative 1.96, and we have 0.025 or 2.5% of the area under the curve of a standard normal probability density function to the right of 1.96, which means in the middle we have 95% of the distribution. So, because the distribution represents 100% of all of the possible values, of a z variable, if we can take these numbers right here and build that interval, then 95% of all the possible values of the z-score, the standardized, z test statistic, or whatever we're going to start calling it here soon, 95% of the time, we're going to get a z-score in between here, right? If hopefully that makes sense. And if we can find some way to take these numbers and turn them back into these numbers, what do we have? Well, we would have, we would have 0.025, 0.025, and 0.95. Basically what we would end up with is if we can find some way to move from these numbers to these numbers, or to go from 0, or the z-scores, back to units of x bar, as opposed to units of standard errors, then we would be able to say, okay, let's take whatever this number turns into and make a little interval out of it, and we'll be able to say there's a 95% chance that the true average number of bananas that an American citizen eats in a year is between this number and that number. Just like there's a 95% chance that any given z-score is going to fall in between negative 1.96 and 1.96. These numbers right here, the 1.96 and negative 1.96, those are called critical values, okay? They help establish the bounds of a confidence interval. How do they do that? Well, let's talk about it, okay? We've talked about picking the critical values. Now, of course, this graph is something I hugely advocate you get used to drawing. Draw the normal graph, or chi-squared, or whatever you're drawing, right? Then draw these little underlined things here, and split them up exactly how you want them split up. So if I say I want a 95% confidence interval, draw this little underneath thing here, draw these two lines, you don't know the numbers yet, but put 0.95. Then go to your table, based on what kind of distribution you're working with, and find these numbers, write those out, if it helps you find the numbers. That's how you pick critical values, okay? How are we going to actually get from critical values to these numbers? Well, we're going to find out, okay? And just one thing really quick, obviously. If I wanted this to instead be a 0.90, a 90% confidence interval, then these numbers would clearly change, right? Because I wouldn't want the numbers that are at the bounds such that only 0.025 or 2.5% of the distribution are outside of them. I would want the number such that, 0.05 or 5% of the distribution lies outside of them, right? I would have to move the numbers. And as my confidence level shrinks, it goes from like 95% to 90%, my interval will also shrink, right? You'd say, well, there's a 90% chance that it's between these two numbers, but if you want to be even more certain, there's a 95% chance it's in between these two numbers, and there's a 99% chance it's in between these two numbers, and there's a 99.5% chance it's between these two, right? So this is the idea of this is how we're picking these critical values to build these intervals, right? So now that we have that out of the way, okay, we've established the idea of what a critical value is, let's actually do something practical and build these confidence intervals, okay? So if I have the following, my x bar was 30. My, see, the trouble is I should have solved for s so that this number works out really nicely. And in fact, we can do that really quick, and then I'll show you how to build the actual interval. So let's say, for example, x bar was equal to 30. We don't know what their sample standard deviation was, but we know that they had, what was it? 5,000 observations in their sample. And that should be pretty much it, right? So we know, well, what we don't know, no, I have to actually give a standard deviation here, huh? Yeah, I actually have to give that, huh? So let's say they had a standard deviation of 1, just to make things nice and simple, right? The standard deviation, their sample standard deviation was 1. They had 5,000 people in their sample, so we're just going to use the z numbers off of the t-table just because that makes it easier, right? And we want to figure out what was the confidence level from their margin, right? Because they gave us 28 and 32. So that means, just like we drew in the last little graph, they gave us a graph such that we had 32, 30, and 28 as the bounds. And what we're really interested in figuring out here is, what were the probabilities on the outside? Question mark, question mark. Or what was just the probability on the inside? That's what we're interested in figuring out. So let's standardize these numbers from the interval. And what that will give us is z-scores, or critical values, that we can then compare to their probabilities and solve this problem, right? So let's go ahead and do that. How did we standardize it last time? Well, we take x bar minus mu over square root of, in this case, s squared over n. But for x bar, instead of using 30, we're just going to use whatever number we were trying to deal with in the first place, right? So let's... And what we're going to do is we're actually going to call mu 30 here, just because that is what we have estimated as sort of our middle point. So that's what we're going to kind of do here, right? We want this number to turn into 0 on the standard normal so that we can figure out what these numbers are out here, if that makes sense. So let's go ahead and do that. First thing I would do, of course, 30 minus 30 over the square root of 1 squared over 5,000. That's going to be equal to 0 because the top is going to be equal to 0, right? So that helps us out as we're building this second graph here, which we're going to really pretend is equivalent. But now we need to do the same thing to these two numbers on the outside so that we can figure out what these probabilities are. Okay? Let's do that. 28 minus 30 over the square root of 1 squared over 5,000. Okay? I'm going to pull out my calculator. There's no reason to do this by hand. 28 minus 30 is negative 2 over the square root of 1 squared over 5,000. Let's calculate that. And that's not right. It should be 1 over 5,000. Calculate. Wow, that is different. Holy moly. Maybe we should make this 2. Let's make it... Nah, you know what? It's fine. Let's just leave it as 1. Okay, calculate that. Okay, negative 141.42. Okay, so negative 141.421. Okay, and then we can do the same thing for 32 minus 30 over square root of 1 squared over 5,000, and that is going to be equal to this but positive, right? Same exact thing, only the positive version, 141.42. And you're going to see in just a second why this is kind of an insane example. This number over here becomes 141.42, and this one is negative 141.42. And let's go to the z-table and see if those numbers show up anywhere. And the answer is, when we get to a z-score of like 3.49, we're already at a probability of 0.9999998, right? That's a problem. So this interval that they're giving us here is actually an insanely large interval, okay? They're saying there's a 99.999999 chance that the true mean falls somewhere in here, that the parameter mean does. Because these probabilities on the outside of these z-scores are basically 0. They're like 0.000001, and even that is probably generous, right? Those are absolutely incredible numbers. But what if, in fact, their standard deviation was much bigger? What if, for example, their standard deviation was 50, right? I don't know how that would be the case with 5,000 observations, but it'd have to be huge, right? Basically, at this point, let's eliminate this and let's actually move away from that for a second, because this example is only helpful to a certain extent because this is not really a practical number, right? Why would they bother giving us an interval that has such a high chance of like this interval has such a high chance of containing the mean that it's almost useless, right? It's almost too big, like it's too wide, right? It's so wide that if I were trying to plan for the 300 million people, if I'm the head of like some banana company and I need to know about average American consumption of bananas for business, this interval is going to be way too wide. They're giving me an interval that's so wide it's almost worthless because, like, for me, like, the difference between 30 and 28 for one person is not big. That's just 2 bananas I have to account for. But the difference between 32 and 28 across 300 million Americans turns into billions of bananas that I need to be ready for. So what I might do if they told me this interval, and I figured out that this was the confidence level associated with it, is I would say, okay, can you please go back to the lab and just give me an interval such that it only has a 95% chance of containing that parameter. I want you to trade off having an absurdly high chance of containing the parameter within this value, within this region right here. I want you to trade that off with narrowing down the interval for me. So I would say, okay, based on your data that you have then, this being the data, what is a 95% confidence level, or confidence interval, right? And let's bring this back over here for just a second. Okay, so here they go. I might say, okay, at this point, you've given me an interval that's just too big. It's not something I can plan with because the difference between the upper and lower bounds of this interval is billions of bananas across the United States when you extrapolate it over the average population, right? So what I want you to do instead, I might tell Ameripol, is I would say, I want you to build me a confidence interval that looks like this, okay? I would like to be built a confidence interval such that the probability the true parameter that you're looking for falls within that interval is just 95%. I'm okay with having a 5% chance of the true mean, the true average number of bananas that a United States citizen eats in a year. I'm okay with a 5% chance of that falling outside of the interval that you give me. But I want the interval smaller so I can plan with it, right? So I want this. That's what I tell Ameripol. And they say, okay, we can make that happen. 0.95. Or if they've given me the data, I can just calculate it myself, right? How would I calculate that? Well, let's go back to the table and say, what if I only want a 95% confidence interval? Well, the nice thing is I have this 95% confidence level column on the T table, and I have the Z star degrees of freedom for basically anything that's bigger than 1,000, and those numbers are 1.96, okay? That Z star score is 1.96. So basically, the numbers at the bounds, this T star and negative T star, or Z star and negative Z star, that will give me 95% in the middle, a 95% confidence interval, are 1.96 and negative 1.96. So let's make that 1.96 and negative 1.96. And now let's say, okay, now that we have those critical values picked, those critical Z scores, those Z scores that will build me my confidence interval at the level that I would like, okay? How does that actually translate, to my real world graph, okay? Let's draw this new graph. And I know I'm still going to have 30 in the middle because that's the average that they gave me, right? That isn't changing here. But I want to move these numbers in a little bit so it's a little bit easier to plan with them. What I already know about this graph that I'm drawing currently is that in this little middle section, we're going to cover 95% of the possible outcomes for mu, or the true average number of bananas consumed by an American citizen every year, right? But I just don't know what these numbers here are. They're not 28 and 32. I can tell you that it's going to be squished in from there, right? because we're going to lower the chance of actually containing the true mean. We're going to take these 141s and push them into negative 1.96, right? So this number is going to have to be moved in, okay? Let's actually figure it out. And the way that you do it is you do the following, okay? How did I standardize something? Well, I took x bar, subtracted mu, divided by s squared over n, the square root of s squared over n, and what that would have given me were these negative 1.96 and 1.96, these numbers in units of standard deviation, standard errors from the mean, right? It's equal to negative 1.96. So all I have to do then, treating m as 30, mu is 30, and using the numbers I was given, 1 squared over 5,000, let me just solve for this number right here, this bananas number, right? If I just solve for that number, this will be the lower bound because I'm solving for the negative 1.96, and then I'll solve for the upper one as well. Okay, how do I do that? Let's do the math. Let's do the algebra really quick. I'm going to just make some room for it. Okay. Well, first of all, I'm going to multiply by the standard error. Okay, so I know that bananas minus 30 is equal to negative 1.96 times the square root of 1 over 5,000, right? Because 1 squared is just 1. And then, to get that lower bound, the lower bananas bound would be equal to 30 minus 1.96 square root of 1 over 5,000, right? And then, if I wanted the upper bound of bananas, the upper bananas bound, bananas is just B-A-N-A-N-A-S, I do know how to spell it, right? Hopefully you can see that instead of negative 1.96, I would put a positive 1.96 right there. So upper bound for bananas is actually just going to be 30 plus 1.96 times the square root of 1 over 5,000. And let's figure out what those numbers are really quick. Okay, 30 plus 1.96 times the square root of 1 over 5,000. And then 30 minus 1.96 times the square root of 1 over 5,000. Calculate. Those are much more useful numbers. And in fact, if I change my settings so I can't even add more decimal points to my calculator. So for all intents and purposes, these numbers will be the same. Although, basically what this, hold on, wait. Oh, that's why they're the same. I got a stray minus in there. I was like, one of them should be bigger than 30, right? There we go. So the new confidence interval would look like this, right? The 95% confidence interval for the true average of number of bananas eaten by an American citizen per year, the interval of numbers that has a 95% chance of containing that true parameter mean looks like this. It's 29.972 to 30.028-ish, right? That is a huge difference from the 28 to 32 margin that we had before. And in fact, this is a much more realistic margin that you would see, right? The margin in this case is the 1.96 times 1 over 5,000, right? Because it's just, here's kind of the generic formula. X bar plus or minus whatever your z or t score or whatever it turns into, plus or minus the z score or the t score, or t, right, times the standard error, the square root of s squared over n, or sigma squared over n, right? That's kind of the basic formula, and this is actually how we figured it out. This is what it turned into, was unstandardizing these numbers right here. Now the difference for me as like a banana company CEO between having to change, because like, just let me show you something for a second, right? 32 times 300 million. 28 times 300 million. Now let's do 30.028 times 300 million. Give me that extra zero. And 29.972 times 300 million. And in fact, it's probably closer to 330 million by now, but dang it. That's so annoying that it does that, right? Before, the difference in bananas that I had to account for was very large, hundreds of millions of bananas that I had to account for in difference. But now looking at this, if I'm okay with adding a little bit more uncertainty, then I get to reap the reward of having a much narrower 29.972 times 300 million. Now the difference between those is only it's only about a million. It's only about 1 2/3 million, right? So instead of having to plan between potential differences in my planning of up to like several 100 million bananas that the United States is going to consume this year, now I only have to plan in between, my upper bound and my lower bound are only separated by about 1 million bananas. And that's way more manageable for me. And that's only because I'm willing to accept a little bit more risk, right? Basically, what a 95% confidence interval is telling me is, look, there's a 95% chance that the average, the parameter from the distribution of how many bananas an American eats each year, there's a 95% chance that the expected value of that distribution is in here, right? We don't know the distribution, we can't see it, but there's a 95% chance that its average lies here. There's like a 99.9999999% chance that it lies in here. All of that, of course, being based on what we saw in the sample, right? Hopefully you can tell that if this number were to have been different, or if this number were to have been different, or if this number were to have been different, these numbers would also be different. A confidence interval says, based on the data that we saw, there is a this percent chance that the true parameter you were looking for is between this number and this number. You find it by taking your critical values, unstandardizing them, put them in brackets. That is a confidence interval. That is what they mean, that's what they do, that's how you build them, okay? So, what we covered today was the fact that there is variance in estimators, even though these two companies use the same estimator. One of them put more people into it, but they both got different numbers, and we didn't know what the confidence level for those intervals was, right? They didn't tell us, hey, there's only a 95% chance that the true parameter falls within here, right? Or like there's almost a 100% chance that it falls in here, because there's never quite a 100% chance, of course, because the world is inherently random and things are wild. But this confidence interval is almost too big, right? If Ameripol had instead given us this confidence interval, this 29.972 to 30.028, they would have said, look, based on the numbers that we saw and the people that we asked and the Americans that we talked to, there's a 95% chance that the true value, the true average number of bananas that an American citizen eats, falls in between these two numbers. And we'd say, whoa, that's a tiny interval. That's super cool. It's basically 30. And if it's not 30, it's really close to 30, That's basically going to cover everything that we need to talk about confidence intervals, okay? It's a little bit interesting to wrap your head around, but basically, we're using known probabilities from a known probability distribution and taking it back to a real-world distribution in real-world units. We're going from critical values to numbers of bananas, okay? That's what a confidence interval does. Again, I highly, highly recommend that you draw these graphs, because these little graphs right here are your key to success in understanding these problems, okay? So that's going to cover everything for today. We're going to go ahead and wrap that up. I don't have the next one prepared, but the next time you come into lab hours, we are going to talk about hypothesis testing, which you will notice once we start talking about it and working through it, is basically the same thing, okay? And we'll show you how that makes sense and why that makes sense. It all comes back to these graphs, okay? But basically, it's the same thing. So next time you come in, we'll talk about hypothesis testing, okay? And we'll cover that on the next mini. Of course, as usual, if you have any questions, if you're in the class, email tmorg.ta@gmail.com. And if you're not in the class, email labhours@tmorg.org. As always, like, share, comment. You know the drill. I'll also answer questions in the comments. And hopefully we'll see you around next time. Thank you so much for stopping by. Have a wonderful day. Peace.